This is my Lab 7 Part 1, and as you can see here, we're trying to calculate the mass of the black hole. We start off with the mass of the star, which is 1.98989 e to the 30th, and the black hole position, which is right there. Now, as we go down, you can see the time step is 86,400 seconds, which is just 1 day in seconds. So we start off and we get our data, the x, y, and positions of the star from the star data at Schwartz-38 GodTech, and we bring them down here to compute the change in x and the change in y, which is just the x final minus x initial and y final minus the y initial. And we use that using the coordinates listed in the data sheet that we downloaded for this lab. Now, the v initial and the v final. We get this by getting the velocity, which is just the change in position over the change in time. So what we do is we take the x value, the delta x and delta y, and we divide them by the time step, which is delta t. Now, this gives us our v initial and v final. Now, our p initial and p final is essentially the same thing, but we multiply it by the mass, and that gives us our initial momentum and final momentum. So, in order to find the change of both these quantities, we just do the p final or v final minus the p initial or the v initial. Now, this gives us our dp. Now, all we have to do is divide it by our time step, and that gives us the change in p over the change in t, which is equal to our f net. Now, the f net is made out of a parallel and perpendicular component. The parallel component, as you can see here, is just the change in magnitude over the change in time multiplied by the direction. And our perpendicular component is f net minus that parallel, or it's just a change in direction over the change in time multiplied by the magnitude of the force. So as you can see here, now we go all the way down, and once we figure out what the p dt is, that's our f net. And there's only one force acting on the star, which is gravity. Sorry about that. So as you can see down here in our equation, gravity, the force of gravity is negative g m1 m2 over distance squared. Now we set that equal to our p dt, and we rearrange it in order to find our mass 1, which is the mass of the black hole. So I'll run it for you. As you can see here, there's 3 arrows, both represent the p dt, and then the p dt parallel and perpendicular. The perpendicular one always points inwards towards the kissing circle, as you saw. And it gave us our values right there. Now, what if we had a different mass of the black hole? Well, and all the other stuff was the same. Could that happen? Well, it couldn't happen, because if our value, the f net, was still the same, like if the distance between them was still the same and the momentum and all that is still the same, then the mass of the black hole couldn't be different, because our force value would still be the same. And if our force value is still the same and all the other variables were the same, you can't change the m1, or the mass of the black hole. Now, if we had a different force or something like that, maybe that could change. Then we can know if the black hole was a different size. But if the f net is still the same and all the other variables are the same, then the mass of the black hole is just not going to change. I hope you liked this video, and thank you for watching.